Alright, in this video we're going to take a look at calculating normal distribution in the real world. And by that I mean that we're not going to find the z-score first. We're actually going to be able to enter in our observed value and then our mean and our standard deviation, and then looking for the area left, right, in between, outside, etc. So again, we can just put it all in at once and without having to convert to z-scores. Although the nice thing is, if you want, you can. So you can convert to z-scores first. All right, so we're going to find the area under a normal curve for an observed value or observed values. And so in our last section, we talked about the standard normal distribution, which has a mean of 0 and a standard deviation of 1. So again, involving z-scores, your mean of all of your z-scores is 0. Your standard deviation of all your z-scores is 1 within a distribution. And here's your equation. F of z equals this scary looking equation over here. And again, we didn't really work with this too much. In more advanced statistical courses, you would work with something like this. And matter of fact, you'd actually work with the one we're going to show you here in this video. So using observed values and x instead of z, and the z-score formula where we can replace a z with x minus our mean divided by our standard deviation, we get the following equation for an observed value x. Bear in mind that the standard deviation when we're looking at z-scores is 1. So it's going to look slightly different even after we substitute this expression in for this z. So here is our normal distribution equation. Again, you're not going to have to really worry too much about it, but the z-scores were a special instance where our mean was 0 and our standard deviation was 1, which again, we could convert our equation here to using z-scores, but we don't really have to do that. Here's what the graph looks like. So we have our mean, again, right in the middle, and then we have 1 standard deviation below, 2 standard deviations below, 3 standard deviations below, and then 1 standard deviation above, 2 standard deviations above, 3 standard deviations above. With the standard normal distribution, this was 0, -1, -2, -3, and this was 1, 2, and 3. So it's the same curve. We're just not using z-scores anymore. So you have the option of converting your observed value to a z-score using the mean that you'll be given and the standard deviation that you'll be given as well. However, most technology allows you to enter in the observed value, the mean, and the standard deviation without having to convert to a z-score first. And in the program we're going to use here, I'll link the code in the description, or a link to the code in the description. It allows you to enter in observed values. So again, you don't have to convert everything to z-scores. So go with what you feel most comfortable with. If you want to convert to z-scores and do it the other way, by all means go ahead. But you will have the extra step involved in converting it to a z-score first. All right, so example 1, we have an air conditioning manufacturer says their machines have a mean cooling capacity of 10,000 BTUs. And due to variations that arise in manufacturing, there's a standard deviation of 400 BTUs. So again, not every single air conditioning unit that comes off the line is going to cool to 10,000, use 10,000 BTUs to cool. There's variation involved, and here our standard deviation in the assembly process or in the manufacturing process is 400 BTUs, or British thermal units. So what is the probability of selecting an air conditioning unit that is 11,000 BTUs or less? So maybe it's a real hot day and your one that you happen to buy is, what is the probability that's 11,000 BTUs or less? So here's 11,000 on the observed values normal distribution. We're looking at the area to the left of that 11,000. So we want to know what are the chances we get an air conditioning unit that is somewhere in this green shaded region. So again, we can use technology for this. In this video, we'll be looking at observed values. So in the last section, we did z-scores, but in this one, we're looking at observed values. So again, it's broken down by necessity of what you have. So we have option 2, and we're trying to find an area that's to the left of that value. So we want option 1. And we're looking for the area to the left, so press 1. And then the observed value, because my memory is not that good, was 11,000. So 11,000. And then the mean was 10,000. And then our standard deviation was 400. And it says the area to the left of 11,000 is 0.9938. So about 99.38% of all air conditioning units from this manufacturing process are going to be 11,000 BTUs or less. So again, we're finding the area to the left, and we got about 0.9938. So about 99.38% chance of selecting an air conditioning unit that is 11,000 BTUs or less. So very, very high chance of that happening. All right, example 1B. What is the probability that you select an air conditioning unit that is between 9,500 and 10,600 BTUs? So in other words, you have between 9,500 here and 10,600 here. What is the area between these two values? What is the probability of getting an air conditioning unit between these two BTU values? So this one, we're going to use X1 for our lower, X2 for our upper, just to have something to note them by. 9,500, 10,600, our mean's 10,000, our standard deviation's 400. So probably not going to remember those values, but let's see. Observed value, so it's 2. And we're trying to find an area, so it's option 1. And this time it's the area between two values, so option 3. And I think it was 9,500 and 10,600, yeah. So 9,500 for our smaller value, 10,600 for our larger value. Our mean was 10,000, and our standard deviation was 400. So the area between that is about 0.8275. So our area between is about 0.8275. So we have about an 82.75% chance of selecting an air conditioning unit from this manufacturer that's between 9,500 and 10,600 BTUs. So, all right, that about does it for this video. Thank you for watching. I'll see you next time.